Okay, now let's do number 90. Now for number 90, this time which is really common, and this is the test question, one of the test questions, is it wants you to draw, no, I want a straight line, um, a phase diagram, and they give you enough data with which to do that. So I'm going to draw my axes out. Okay, and for this time it wants bromine, and it says, for read the question number 90 on page 505, it says, like most substances, bromine exists in one of the three typical phases. Diatomic bromine has a normal melting point of negative 7.2 degrees Celsius and a normal boiling point of 59 degrees Celsius. Triple point for bromine is negative 7.3 degrees Celsius and 40 torr. Critical point is 320 degrees Celsius and 1 atm. Using this information, sketch a phase diagram based on the points above. Based on your phase diagram, order the three phases from least dense to most dense. What is the stable phase of bromine at room temperature and 1 atm? Under what temperature conditions can liquid bromine never exist? And what phase changes occur as the temperature of a sample of bromine at 0.10 atm is increased from negative 50 degrees Celsius to 200? Okay, how do we do that? Well, first off, we need to set up our graph. And remember, these are rough sketches. They're not to scale, but you're going to use the data they gave you to come up with some shape. And we do have some general idea about what it should look like. Okay, so we've got pressure in degrees Celsius. I forgot this on my last one because I was copying it from the book. And ATMs. All right, I'm going to go ahead and put in my dotted line kind of, sort of in the middle-ish. Oops, might as well let it help me. All right, let's do a nice dotted line here. There we go. Okay, so I'm going to get my dotted line. I'm going to use that to represent my 1 atm of pressure. I want a regular old. Okay, so there's my 1 atm right there. All right, now the next thing in terms of information in order to plot, if I think about my temperature ranges, now remember, if we think about pressure ranges that they gave us too, values they've given us are 0.05. The other number they've given us is 100. So clearly I'm not worried about this being to scale. I'm just showing them that I know the numbers that they gave us and I'm going to use it to sketch my graph. Same thing down here on the x-axis. Okay, the values they gave me for temperatures go from negative 7.3, negative 7.2. Let me try to get these a little closer. Make that negative 7.3. This negative 7.2, and maybe even a little bit further over. Clearly you can see it's not an exact science, but we can still have some definite shapes here. Then we're going to jump to 59, and then we're going to jump out here to 320. I'm going to go ahead and extend my line just a little bit to make sure I can get all that in there. Same thing here. Okay. So now let's go about trying to sketch these things. All right, one of the points that they gave us, okay, was, notice this is ATM, so I went ahead and converted 40 torr to 0.05 ATM. That's where that came from, sorry. Would have helped if I told you that. Okay, but they told me that the triple point is going to be at negative 7.3 degrees Celsius and 40 torr. So that right there, my friends, is going to be the triple point. Okay, then the next value that they gave us is it has a normal melting point of 7.2. So I know if this is my 7.2 value, means the normal melting point is going to be at 1 atm. All right, and then the next value they gave us is the normal boiling point, which is going to be 59 and 1 atm. And then lastly, what they told us, the critical point is 320 degrees Celsius and 100 ATMs. So let me come up here, and then I'll show you how we make these shapes. All right, so I'm going to kind of start off with just a curve that's going to go up through the triple point and up through the melting point. And that's going to give me, let me do this a little bit better than that. That's going to give me my border between the solid and the liquid phases. Okay, so that's my first border. It goes up through the triple point and then through the melting point. Then the next line I'm going to draw is going to go from the triple point through the boiling point and through the critical point. That's going to give me my border between my liquid and my gas. And a lot of times you'll see, oh, I guess it's good practice to maybe connect some lines that show that you know where these values go. So for example, clearly I didn't go totally straight all the way over there, but that's showing me my critical point. Here is my typical melting point, and here's my typical boiling point. So it just shows some of those connections. All right, now we can go and make an attempt to answer some questions that we have based on these things. Okay, first of all, in terms of density, it's going to be our typical least dense to most dense. We're going to go gas to liquid and then solid. And the reason I know that is simply because there is a positive slope to the the liquid and solid border. If it was a negative slope, it would be the opposite. The liquid and the solid would be inverted, but that's going to be that one. So that's the first part. The stable phase of bromine at room temperature. Room temperature is usually about around 25 degrees Celsius. A lot of the labs we've done, we've measured it at 22, 23 degrees Celsius. So maybe around 22 degrees Celsius is probably a better indicator on that, but you know, somewhere in that 22, 23 range. So if we look on our graph, somewhere between 22 and 1 atm, it's going to be a liquid. Also, if we know anything about bromine itself, it's the only nonmetal that's a liquid at room temperature. It's one of the only elements that's a liquid at room temperature. So that makes sense based on our graph. Another thing, under what temperature conditions can liquid bromine never exist? From a temperature standpoint, it cannot exist at a temperature that is below the triple point of negative 7.3. So it can't be a liquid below negative 7.3 degrees Celsius, and it also cannot be at a temperature above the critical point of greater than 320 degrees Celsius. So those are kind of the borders, right, of our liquid phase, and that's also what our graph is looking at on these. And finally, it says what phase changes occur as the temperature of a sample of bromine at 0.10 atm. So it's going to be somewhere around here, is increased from negative 50, so way down here, let me do this in a different color, okay, from maybe right about here, negative 50 to, we're going to 200 degrees Celsius, so kind of this. And I realize that's not even a straight line, but you kind of get the picture. So if we had to follow that path, it would just follow our typical pattern where it would go from a solid, and then it would it would melt and gain enough energy in order to go into a liquid. Oops, sorry, it's still my dotted phase. So the last one, rather, would go from a solid to a liquid to a gas. No funky sublimation or deposition, because it's going to pass right through all three of those phases. So hopefully phase change graphs are a little bit less scary, and let me know if you have questions.